Hello everyone, a very warm welcome to Smiley Kids channel. Today we're going to deal with the topic real numbers. Exercise 1.1 and 1.2. So let's begin. Question number 1. Express each number as a product of its prime factors. In that we have the first sub-question as 140. Now in order to express 140 as the prime factors, we are going to find out the prime factorization of 140. Now 2 times 7, 0, isn't it? Now 2 times 3, 5. Now 5 times 7. Then 7 times 1. Now we know that the prime factors of 140 are 2 into 2 into 5 into 7. Now I have expressed 140 as the product of its prime factors. Therefore, the prime factorization of 140 is 2 times 2 times 5 times 7. This can also be expressed as 2 square because 2 times 2 is nothing but 2 square. Now 2 square into 5 into 7 will be the product of prime factors. Therefore, the prime factorization of 140 is 2 square times 5 times 7. In that, we have the next sub-question, that is 156. Now we'll find out the prime factorization of 156. Right, 156. Now we know that it is divisible by 2. So 2 times 7, 8. Then 78 is again divisible by 2. 2, 3, 6. Then we are left out with 18. So it's 39. Now we know that 39 is not divisible by 2. Rather it is divisible by 3. So 3 times 1, 3. And then we have 13. Now we also know that 13 is a prime factor. So 13 times 1. Now what will be my prime factorization of 156? Well, that's right. 156 is equals 2 times 2 times 3 times 13. Now come on, tell me what this is. It is nothing but 2 square times 3 to the power of 1 and into 13 to the power of 1. It's not required to mention to the power of 1 since it means the exact same thing. Therefore, the prime factorization of 156 is 2 square times 3 times 13. Now we have the third sub-question over here which says 3825. Now, that's a huge number. Right, now let's find out the prime factorization of this number. 3825. The number clearly says it is not divisible by 2 at all. Now tell me, is it divisible by 3? Let me check. 3 plus 8 plus 2 plus 5. Wait, what? What am I doing? In order to find out the prime factorization of this number, first I need to find out the number which is divisible by this. Now, we have already known that the number 2 cannot be a prime factor of it, isn't it? So, I'm trying to check whether 3 is going to be a prime factor of it. Now, what is the divisibility rule of 3? The sum of all the numbers will give you such a number which is divisible by 3. If it is not giving you, then it is not divisible by 3. Now, 3 plus 8 is 11. 11 plus 2 is 13. 13 plus 5 is 18. Now, is 18 divisible by 3? Obviously, yes. So, the given number is divisible by 3. Now, 3 times 1, 3 times 2, 3 times 7 and 3 times 5. So 1, 2, 7, 5. Now you tell me, is this number divisible by 2? Not at all, isn't it? Is this number divisible by 3 by the way? Let's check. 1 plus 2 plus 7 plus 5. What is 1 plus 2? 3. 3 plus 7 is 10 and 10 plus 5 is 15. Now Is 15 divisible by 3? Yes, it is. So it is divisible by 3. 3 4s 12, 3 2 6 and 3 5 15. So we have 425. Now is 425 divisible by 2? Not at all. Is it divisible by 3? Let's check. The sum of the numbers must be divisible by 3. So 4 plus 2 is 6, 6 plus 5 is 11. Is 11 divisible by 3? Not at all. So the given number will not be divisible by 3. So let's check out with the next prime number, that is 5. Obviously yes, right? 5 is definitely a prime factor of this number. Now 5 times 8 and 5, 85. Now is 85 divisible by 2? Not at all. Is it divisible by 3? What is 8 plus 5 equals? It equals 13. Is 13 divisible by 3? No. So the given number may not have the prime factor of 3, right? So 85 must be again divisible by 5. So 5 times 1, 17. Again 17 times 1, because we know that 17 is a prime factor. How easy it was. So it is important to know the divisibility rules to solve the bigger numbers like this. Now what will be the prime factorization of 3825? So 3825 is equal to 3 into 3 into 5 into 5 into 17. Now what is this also expressed as? It can be expressed as 3 square times 5 square times 17 to the power of 1. Therefore, the prime factorization of 3825 is 3 square times 5 square times 17. Now we have 5005. The prime factors will be, now we have 5 times 1001, and then we have 7 times 143, and then we have 143, which is divisible by 11, right? So 11 times 13 and 13 times 1, isn't it? So the prime factorization of 5005 is 5 times 7 times 11 times 13. Then we move on and solve 7429. Now this number is not divisible by 2, 3, 5, 7, 11, 13, but this number is divisible by 17. So 17 times 4, 3, 7. Then we have 19. 19 times 23. Then 23 times 1, because 23 is a prime factor. Now come on, tell me, what is the prime factorization of 7429? It is 17 times 19 times 23, isn't it? Now let's move on. Question number 2. Find the LCM and HCF of the following pairs of integers and verify that LCM into HCF is equal to product of two numbers. Now what are the two numbers on my screen? They're 26 and 91. Now in order to find the LCM and HCF, we must first find out the prime factors of the two numbers. So 26 ka prime factorization will be 13 times 2, isn't it? And then what is the prime factorization of 91? Come on everyone. It is 13 times 7. Now what is the LCM of these two numbers? LCM of 26, 91 will be the product of the greatest powers, isn't it? And we observe that in this case the LCM will be equal to 13 times 2 times 7. Alright, now what is this equal to? 13 times 2 times 7 is equal to 182, isn't it? Then we have HCF of 26 and 91. What is HCF? Come on. HCF is a product of the lowest powers and the common factors, in fact. Now we observe that the common factor in both the cases is 13. So what is the LCM of 26 and 91? We got it as 182. And what will be the HCF of 26 and 91? It will be equal to 13. Now 182 is the LCM and 13 is the HCF of 26 and 91. Wait, what? The answer is not yet done. We have still more to do. Now record the observations. We know that LCM is what? 182. And what is HCF? 8. It is 13, isn't it? Now we're going to verify that LCM into HCF is equal to product of two numbers. Right. Now LCM into HCF is equal to product of two numbers. Now what is LCM? 182. What is HCF? 13. What are the numbers? 26 and 91. It's product. Now what is 182 times 13? It is equal to 2366 or 2366, isn't it? And now we're going to find out the product of two numbers, that is 26 times 91 in this case, which again is equal to 2366. Now we have verified the relation that HCF times LCM is equal to product of two numbers. Hence verified. Isn't it? Then we have the second pair of numbers 5, 10 and 92. First let's find out the prime factors of each. 5, 10 and 92. The prime factors of 5, 10 are 2 times 3 times 5 times 17. The prime factors of 92 are 2 times 2 times 23. Isn't it? Now this is nothing but 2 square times 23 to the power of 1, and this is nothing but 2 to the power of 1 times 3 to the power of 1 times 5 to the power of 1 and 17 to the power of 1. Now what is the LCM of 5, 10 and 92? So we have 2 times 3 times 5 times 17 times 23. Wait, it's not yet done. All these numbers are the numbers which are in the given two prime factorizations, isn't it? Remember that LCM always consists of all the numbers included in the prime factorization of both. Alright. Now, we have 2 whose highest power is 2, isn't it? 1 is greater or 2 is greater? 2 is obviously greater than 1, isn't it? So it is 2 square times, and we have 3 to the power of 1, 5 to the power of 1 and 17 to the power of 1 as the highest powers in fact. So they'll be obviously the same, and 23 also has the highest power as 1. Now what is this all equal to? 2 square times 3 times 5 times 17 times 23. It is equal to a vast number 23,460. Wait, this is the LCM of 5, 10 and 92. We are yet to find out the HCF of it. HCF will be the product of the least powers of the common factors, isn't it? Now the HCF of 5, 10 and 92 will be equal to 2. Just observe. The only common factor you can find out in the prime factorization of both is 2. And we observe that 2 to the power of 1 is there and 2 to the power of 2. But we are finding the HCF. HCF means what? Product of the least powers. So 1 is less than 2. So it's 2 to the power of 1, which is 2. Therefore, the HCF of 5, 10 and 92 is 2. Now record your observations again. LCM is what? 23,460 and HCF is 2. Erase. Ta-da! Everything is gone. Now let's verify the relation of the HCF and LCM, which is equal to product of two numbers. Now what is our LCM? 23460 times 2 is equal to 510 times 92. Let's see if these both match. This is equal to 46920, and well, yeah, this is also equal to the same thing, 46920. Now we have successfully verified the relation that HCF times LCM is equal to product of two numbers. Then we have the next pair, which is 336 and 54. Now let's find out the prime factors of each of them. 336 equals 2 to the power of 4 times 3 times 7. And 54 equals 2 times 3 cubed. Now let's find out the HCF and LCM of them. Now what will be the LCM of 336 and 54 equal to? It will be equal to the product of the highest powers. First of all, I'll write all the numbers included in the prime factorization of both the numbers, right? So 2 times 3 times 7. Only 3 numbers are included, right? Now let's find out the highest powers of each. 2 ka highest power is 4. And what is the highest power of 3? The highest power of 3 is 3 itself. Then we have 7, whose highest power is 1. Now the LCM will be equal to 3024. Now, wait, we are yet to find out the HCF of the numbers. Now, what is the HCF of the numbers? The common factors, and we clearly are able to look that 2 and 3 are the common factors, and we are going to find out the product of their least powers. So HCF of 336 and 54 will be equal to what? 2 to the power of 4 is greater, or 2 to the power of 1 is greater? 2 to the power of 4 is greater, isn't it? So we're going to consider 2 to the power of 1 because it is less than 2 to the power of 4. Then we have 3, which is less than 3 cubed. So it is 3 to the power of 1. Now what is 2 times 3? Come on, it is 6, isn't it? Now record your observations because we're going to erase them. Now let's verify the relation, right? So 3024 times 6 is equal to product of two numbers, which is 336 times 54. Let's verify that. Well, 18144, and again we have 18144. Well, again we have verified the relation that LCF times HCF is always equal to product of two numbers. Now we here have another set of numbers 12, 15 and 21, right? We're going to find out the LCM and HCF by applying the prime factorization method. Now, in order to find the prime factors, we're going to apply the prime factorization method, isn't it? So 3 times 4, 2 times 2 and 2 times 1. It is 2 square into 3 to the power of 1. Isn't it? Then we have 15, whose prime factorization will go like this. 3 times 5, 5 times 1. That means 3 to the power of 1 times 5 to the power of 1. And then we have 21, whose prime factorization will go like this. 7 times 3 and 3 times 1. That is 3 to the power of 1 times 7 to the power of 1. Now upon the prime factorization of all the three numbers, we're going to find out the LCM and HCF. LCM of 12, 15, 21 will be equal to what? The product of the greatest powers, isn't it? So 2, 3, 5 and 7 are common in all the cases. And we know that the highest power of 2 is 2 itself, and then we have 2 square times 3 times 7 times 5. Now what is this going to result you in? That is equal to 420. And then we have the HCF of the three numbers 12, 15 and 21, which is What is HCF basically? It is the product of the smallest powers and the common factors, in fact. Right. Now we observe that 3 is common in all the cases, isn't it? And its least power is 1. So 3 to the power of 1, which is 3. Therefore, the HCF of 12, 15 and 21 is 3, whereas the LCM is 420. Well, look at this. All the given numbers, that is 17, 23 and 29, are prime numbers themselves. So we know that LCM will be what? LCM will be product of all the numbers 17 times 23 times 29. Now what is this product equal to? It will be equal to 11,339. And come on, I need not tell you about the HCF of these numbers. The HCF of any prime factors will be definitely 1. That's because all these are prime numbers. And we know that they don't have any number in common. Therefore, the HCF will be equal to 1. Then we have the next one, 8, 9, 25. Let's check this out. 8, 2 times 4, 2 times 2 and 2 times 1. 9, 3 times 3 and 3 times 1. 25, 5 times 5 and 5 times 1. Now, LCM will be equal to 2 cube times 3 square times 5 square, isn't it? 8 times 9 times 25. Now 72 times 25, which is 1800, isn't it? Now what is the HCF of these numbers? We find that there is nothing common out of all these three prime factorizations. So what is the HCF? It is equal to 1. As simple as that. Then we have the fourth question, which says, given that HCF of two numbers is 9, find the LCM of the two numbers. Here comes our relation, which says LCM times HCF is equal to product of two numbers. Now what is the HCF and LCM? It is known for us that the HCF is 9. And we're unknown about the value of LCM, and that is what the question asks us. And we know that LCM times HCF is equal to product of two numbers, and unknowingly or unfortunately the two numbers are already with us. So only unknown value is LCM. So it is 306 times 657. Now LCM will be equal to 306 times 657 upon 9. You know what this will be equal to? This will be equal to 22,300. Wait a second. It is 22,338. Therefore, the LCM of 306 and 657 is 22,338. As simple as that. Then we have the fifth one, which says, check whether 6 to the power of n can end with the digit 0 for any natural number n. See, it's a very simple logic here. For any number to end with the digit 0, right, we need the prime factors as 2 and 5. For any number to end with 0, the prime factors must be 2 and 5, isn't it? Now 2 times 5 is what? 10, isn't it? And it's resulting with 0 as its end of the digit, isn't it? Now, here the question asks, can 6 power n end with 0? We know that the prime factors of 6 are what? 2 and 3. But according to what we know, for any natural number n, right, 6 to the power n can never end with 0. That's because we know the fact that for any natural number to end with 0, we must have 2 and 5 as its prime factors. Now you might tell me that, okay, fine, we have 2 as a common factor. But wait, 5 is not at all a prime factor of 6, isn't it? So, 6 to the power of n can never end with a digit 0 for any natural number n. That's because the prime factorization of 6 does not contain the number 5. As simple as that. Explain why 7 times 11 times 13 plus 13 and 7 times 6 times 5 times 4 times 3 times 2 times 1 plus 5 are composite numbers. Now before we proceed with the question, what are composite numbers? Any number which can be expressed in the form of its primes or in the product of its primes is termed to be as a composite number. And we observe that the first expression is resulting me 1014 and the second expression is resulting me 5045. And both of these two numbers can be expressed as a product of prime factors, isn't it? And since they can be expressed in the product of the prime factors, the numbers 1015 and 5045 or the expressions given in the question are definitely composite numbers. That's because they can be expressed as a product of primes. Now we have the 7th question and the last one, which says there is a circular path around a sports field and Sonia takes 18 minutes to drive one round of the field, while Ravi takes 12 minutes for the same. Suppose they both start at the same point and at the same time and go in the same direction. After how many minutes will they meet again at the starting point? Here, they're asking that there are two people, Sonia and Ravi. And it's been said that there is a circular path like this. Now, it's been said that Sonia, let's suppose say this is Sonia and this is Ravi. Right. Sonia takes 18 minutes to drive one round of the field. That means to make an entire round and come back to the same position, she's taking 18 minutes. Whereas in the exact same direction and starting from the exact same point and starting at the exact same time, Ravi takes just 12 minutes. Now the question asks, after how many minutes will both Ravi and Sonia meet again? So in this case, what will we do? We are going to perform the LCM of the numbers. Always remember the questions like at the same time or at the starting point or simultaneously. All these are keywords that you must remember while finding out the LCM. Alright. Now, in order to find the LCM, first I'll find out the prime factors. The prime factorization of 12 will be what? 3 times 2 times 2. And that of 18 will be 3 times 2. This will be equal to 3 to the power of 1 times 2 square. And this will be equal to 3 square times 2 to the power of 1. Now tell me, what is the LCM of these two numbers? LCM will be equal to product of the greatest powers, isn't it? Now, we know that LCM of 12 and 18 is what? The given two numbers are 2 and 3 in the prime factorization, and we are aware that 2 is greater than 1 and 2 is again greater than 1. So 2 square times 3 square will result to 36, and remember to put on the units, that is 36 minutes. Therefore, After 36 minutes, Ravi and Sonia will meet again at the starting point. Now let's move ahead and solve exercise 1.2. Question number 1. Prove that root 5 is irrational. In order to prove any number to be an irrational number, we're going to first take the number and assume that so and so number is rational number. And such a method is termed to be as the contradiction method. So here we are asked to prove that root 5 is irrational. In order to prove that root 5 is irrational, first we are going to agree or assume to this fact that root 5 is a rational number. We're going to assume to the contrary that root 5 is a rational number. Now, it is an obvious fact that if any number is a rational number, it can be expressed in the form of P upon Q. So, root 5 can be written as P upon Q. Now, when I take the Q to the other side, it becomes Q root 5 is equal to P. Now, this is what I got. Upon arriving to such an equation, I am going to perform squaring on both sides. Squaring on both sides, that means either of the sides of both the LHS and RHS of the equation must be squared. That means Q root 5 whole square is equal to P whole square. This is what it means when I say squaring on both the sides. Now this gives your result 5Q square, because root 5 whole square is 5 and Q square is definitely Q square, isn't it? So it is 5Q square is equal to P square. Now look at this, 5Q square is equal to P square. So here we can write that P square is divisible by 5, and when P square is divisible by 5, definitely P will also be divisible by 5. So it is P is divisible by 5. Now I'm going to assume or let P is equal to 5m. Now why have I taken only 5? That's because here we are asking to prove that root 5 is irrational. If it is, suppose, let's say root 3 is irrational, then it will be P is equal to 3m. If I was asked to prove that root 2 was irrational, then let P is equal to 2m. But here we have proved that root 5 is irrational. So let us assume that P is equal to 5m. Now, when P is equal to 5m, what will P square be equal to? 5m whole square, that is equal to 25m square. Now, why did I do P square? That is because I want to substitute the value of P square in equation number 1. That is 5Q square is equal to P square. Now, I'm going to substitute P square in equation number 1, which is going to result me 5Q square is equal to what? 25m square. Now, if I send the 5 to the other side, it becomes 25m square upon 5, which is going to give us 5 times 1 and 5 times 5, isn't it? That will result you Q square is equal to 5m square. Now, what are you going to write? Q square is divisible by 5 and Q is divisible by 5. That will be your next step. We arrive to this fact that Q square is equal to 5m square. Now, Q square is divisible by 5. And Q is also divisible by 5. Now wait, what? We understood the fact that root 5 is written in the form of P by Q. where P and Q are co-prime numbers. But what is this? This contradicts our fact that P and Q are co-prime numbers because both P and Q have at least 5 as the common factor. But this contradicts the fact that P and Q are co-primes. Hence, this is a contradiction which has arisen due to the false or incorrect assumption that root 5 is rational number. Hence, the given number root 5 is irrational number. Prove that 3 plus 2 root 5 is a irrational number. Now, first we're going to assume to the contrary that 3 plus 2 root 5 is rational. So it can be expressed in the form of P by Q. Now when I send this plus 3 to the other side, it turns out to be minus 3. So 2 root 5 is equal to P by Q minus 3. Now I'm going to find out what? I'm going to find out the LCM. So 2 root 5 is equal to P minus 3Q upon Q, since Q is the LCM of Q and 1. Now when I send this 2 to the other side, so it becomes division, isn't it? It is in multiplication. When it goes to the other side, it turns out to be division. Now P minus 3Q upon 2Q, because 2 here has come to divide. Now have a look at this particular equation. We observe that the RHS, that is P minus 3Q upon 2Q, is a rational number. Why is it a rational number? Because P and Q are integers, isn't it? But when you look at the LHS, we know that root 5 is what? It is an irrational number. How can an irrational number be equated to be a rational number? Isn't it? This is a contradiction which has arisen due to the incorrect assumption that 3 plus 2 root 5 is a rational number. So we conclude that 3 plus 2 root 5 is a irrational number. Prove that the following are irrationals. First one, 1 upon root 2. Now first we are going to assume to the contrary that 1 upon root 2 is a rational number. So 1 upon root 2 can be written in the form of P by Q. Now upon cross multiplication, we get Q is equal to root 2P. Now when I send P to the other side, it becomes Q upon P is equal to root 2. But wait, what? Here Q upon P, where Q and P are integers, turns out to be a rational number. But when we have a look at the RHS, we are able to see that root 2 is a irrational number. So this is a contradiction to the fact that 1 by root 2 is a rational number. So we conclude that 1 by root 2 is irrational. Seven root 5. Again the same procedure. Let us assume to the contrary that 7 root 5 is a rational number. Hence it can be expressed in the form of P by Q. Now when I send this 7 to the other side, it turns out to be division, right? So root 5 is equal to P upon 7Q. Now wait, what? Have a look at the RHS. We are able to see that P upon 7Q is a rational number because P and Q are integers. Now what about the LHS? Root 5 is an irrational number. Again, it is a contradiction, isn't it? This contradiction has arisen due to the incorrect assumption that 7 root 5 is a rational number. So we conclude that 7 root 5 is an irrational number. Six plus root 2. Again, 6 plus root 2 has to be equated to P upon Q because we are assuming to the contrary that 6 plus root 2 is a rational number. Now, When I send this 6 to the other side, it turns out to be P by Q minus 6, isn't it? So root 2 is equal to P minus 6Q upon Q on taking the LCM. Now, have a look at this particular equation. So 1 on the LHS is a irrational number, right? Root 2 is an irrational number. But have a look at the RHS. Where P and Q are integers, P minus 6Q upon Q turns out to be a rational number. But wait, what? It again contradicts our fact that 6 plus root 2 is a rational number. So we conclude that 6 plus root 2 is an irrational number. Oh, that's the end of the video. And before you leave, please definitely subscribe to Smiley Kids channel and hit the bell icon for all the updates and watch our next videos too. Thank you so much.